Number 42. The escape velocity of any object from Earth is 11.2 kilometers per second. Letter A. Express this speed in meters per second and kilometers per hour. All right, so this is just a blast from the past, right? 11.2, we got to convert now kilometers per second into first meters per second. So kilometers has to cancel, they go on the bottom, meters on the top. 1 kilometer, there are 1,000 meters. Notice how the kilometers will beautifully cancel, and now we are left with then meters per second, right? So this just works out to be now, you could just simply 11,200 if you wanted meters per second, all right? And now I would do the same thing, or not the same thing, but very similar process here, where now we're going to do 11.2 kilometers per second, and somehow we now need to convert this in kilometers per hour. I need to get rid of the seconds. So the seconds actually must go in the numerator this time because they originate in the denominator. And now I'm thinking, do I know a relation between seconds and hours? And we actually do, right? You may remember this, that 1 hour is equivalent to 3,600 seconds. If you didn't know that, not a big deal. You could have converted to minutes and then to hours. We would have come up with the same answer. So now this we probably should do in the calculator, 11.2 times 3,600. And we get now 40,000. I don't really care about sig figs right now. 40,320. And that's going to be then kilometers per hour. So those should be the two values there for letter A. Let's take a look at letter B. At what temperature would oxygen molecules, which have a molecular mass they're telling us of 32 grams per mole, have an average velocity of root mean square velocity, that is, equal to Earth's escape velocity of this? All right. So essentially what we need to do is we need to find a formula that relates temperature to the root mean square velocity. That's what we need. Okay. So for letter B down here, I'm going to introduce this formula that the root mean square velocity, so V sub RMS, is equal to now the square root of 3 multiplied by the Boltzmann constant multiplied by the temperature all over the mass of a single molecule. If you're wondering where this came from, I'm going to leave a link in the description below to my general video on the kinetic theory of gases where I talk all about it. All right, so please check that out. So now what I need to do is solve this thing. We're finding the temperature, right? And look, notice this equation relates velocity to temperature. That's exactly what I want. So solving this for temperature, I have to square both sides, right? So if I square the left here, I square the right, we realize that we have V squared. I'm just going to leave, whatever, I'll put VRMS in here. And that will then equal now 3KT all over M. Okay, and now what I need to do is solve this for M, right? So what I'm going to do is, let me just copy this 1 second. All right, so copy. I'll paste it over here. Now all I need to do is solve this thing for T, meaning I got to get rid of the 3, the K, and the M from the right-hand side. So simply just do this switch. Whatever's in the denominator on the right, bring up into the numerator on the left. Whatever in the numerator on the right, bring down into the denominator on the left. Put your little division sign there, and voila. You just solved. And here's now the formula. Okay? So this is saying that we need to know the mass of a molecule or the mass of an atom, depending upon what we are talking about. We're talking about oxygen, and oxygen exists as oxygen molecules, O2. So we would have to find the mass then of a molecule. All right, multiplying it by the root mean square speed, and we already found that. The root mean square speed actually has to be in meters per second. Okay, so that was, I guess, part of the reason for part A. And then K is just the Boltzmann constant. So really what I need to do first is I need to convert now this mass essentially per mole of oxygen molecules. So we have 32 grams per 1 mole. Anytime you have per something, it's per 1 of that something. So remember, mass in physics is in kilograms. So the first thing is I have to convert grams into kilograms. Grams on the bottom, kilogram on the top. There's 1,000 grams for every 1 kilogram. See you later, gram. Then I would now have kilogram per mole, but I don't want kilogram per mole. I need really kilogram per molecule. So I have to put the moles in the numerator now because they have to cancel. The moles started in the denominator, and therefore I have to place them now in the numerator so that they cancel. And now I'm thinking, do I know a relationship between moles and molecules? And we do, right? This is Avogadro's number, 1 mole for every 6.02 times 10 to the 23rd molecules. And see you later, mole. And now what we have left is we're going to have the kilograms per molecule. That's what we need to know in order to plug into the formula. So we'll take 32 and now we'll divide it by, in parentheses, 1,000 multiplied by 6.02 times 10 to the 23rd. And voila, we get 5.32 about, if I round, 5.32 times 10 raised to the negative 26. And that is going to be kilogram per molecule. Okay. Now, I mean, the unit that we're just going to place into this formula is just kilogram, but we needed to find the kilogram per molecule, right? Or the weight of a single the weight of a, I said weight, I meant mass, the mass of a single molecule. All right. As if this isn't confusing enough when I use all those terms all over the place. I'm sure that I'm actually just trying to make it tougher for you, right? If I make it tougher for you, that means the test will be so much easier and stuff, right? So let's plug in that mass. So we have 5.32 times 10 to the minus 26 multiplied by that root mean square velocity. We needed it in terms of meters per second, so we had 11,200. Square that bad boy. And then divided now by 3 multiplied by the Boltzmann constant, which is 1.38 times 10 to the minus 23rd. And we will get our answer. So I'm going to use this exact value here for the mass, multiply that by 11,200 squared. Divide that now by, in parentheses, 3 times 1.38 times 10 to the minus 27. Not 27, sorry, 23. Whoops. And hopefully I did that all right. And I get a value here of about, so the temperature here is going to be quite high. So we get a value of 1.61 or so times 10 to the, what's that, 345. And that's in terms of Kelvin. Okay. That would be the temperature. Hopefully this helps, guys. All right. If it did, please help us out. Subscribe. That'd be awesome. And tell your friends if you find these videos helpful and they're free. It can't hurt to tell some of your classmates. All right, guys. Thank you very much. Take care.